coming. It's a great pleasure to contribute to this technical committee. So yeah, as you heard this, my name is Emilio Martínez-Pañeda. I'm a senior lecturer, associate professor at Imperial College London. And I'm going to talk today about the role of plastic strain gradients of metallic fracture. And this is work that I've done mostly with Fleck during my time in Cambridge, but also through one of my PhD students, Emilio. So we did this roughly 3 years ago, but of course because of COVID, I never got the chance to present it, so I really look forward to your feedback. So I think the main motivation for our work is that we are unable to understand how cleavage or brittle fracture can happen in the presence of plasticity. And this is of course not something that happens often. As you know, when you test metals in a lab, they normally fail in a tactile manner. But there's quite a number of experiments that show that you get brittle fracture, atomic decohesion, quasi-cleavage in the presence of plasticity. You can see this, for example, when you have cracks along B-material interfaces, so a crack growing between a metal and a ceramic, for example. You can see this also when you have metals that are brittle. For example, they can be brittle due to the presence of hydrogen. We have an entire session in this conference about how metals can be brittle with hydrogen. Or you could also see this, for example, in low temperature ferritic steels, when you see cleavage as well. And the reason why we cannot understand this, or we cannot have a mechanistic interpretation of this, is the fact that whenever you want to get brittle fracture or atomic decohesion failure modes, as you see in some of these experiments where you see lots of plastic dissipation, but at the same time very clean fracture surfaces. So the reason we cannot understand it is because you need very high stresses to achieve this. So the theoretical lattice strength is on the order of 10 times the yield stress. The grain boundary strength is 9 to 10 times the yield stress. So how can it be that we get those very high stresses that we need for these brittle interfaces to break down? And we cannot understand it because if you use conventional plasticity theory like Mises and you plot your stresses ahead of your crack, you will see that you get a maximum stress that is 3-4 times the yield stress. I've taken this picture from Bob McMeekin's 1977 paper. So this is the first paper using finite element analysis and large strains to look at cracked fields in elastoplastic solids. And you can see that he predicted that the maximum stress level was 3 times the yield stress. And this can change a little bit when you add some hardening and so on, but it's typically between 3-4 times the yield stress. So the question that we don't understand is, okay, we see in the experiments that we have a brittle fracture process, so somehow we're hitting this cleavage strength, but the maximum stresses that we're predicting with conventional plasticity is 4 times the yield stress. So there must be another source that is bringing those high stresses from somewhere. And there's quite a lot of work that has been done in trying to understand this, and I think there's multiple hypotheses out there. One of the most popular ones, I think, is the one by Sigan Su and his group in Harvard, where they claim that there's a dislocation-free zone. So you have a dislocation-free zone near your crack tip where your stresses can be much higher. This is the so-called SSV model. However, we do think there's a more relevant hypothesis behind this that is more meaningful over the length scales that are relevant for this fracture process, which is the role of these plastic strain gradients and essentially the dislocation hardening mechanisms that are associated with plastic strain gradients, plastic compatibility, GMDs, and so on. So let me tell you a little bit of this. So the main motivation for this hypothesis comes from the strong size effect that you see in metals. Whenever you test metals at the micro scale, you see a smaller is a stronger effect. And you can see this consistently when you do an augmentation, microbending, microtorsion. I'm going to show this classic example that I like very much. These are experiments on thin copper wires. And as you can see, they tested them both under uniaxial tension and in torsion. And these are, as you can see, the torsion quantities, the torque has been normalized. So these are both kind of stress strain curves. Now what you see is that they tested the wires of different diameters, so different sizes of the wires, and you can see that in uniaxial tension, when you have uniform strains, the response, the stress strain curve that you get is more or less independent on the size of the wire, as you would hope and expect. However, whenever you have torsion, where you have gradients of plastic deformation and uniform plastic deformation, you see that those stress strain curves no longer fall on top of each other, and you get a very significant strengthening effect with decrease in the size of the wire. So you get this smaller is a stronger effect that you observe in metals. And the reason you get this is associated with what we call geometrically necessary dislocations, GMDs. So whenever you have plastic incompatibility, you need to generate these GMDs to accommodate the plastic incompatibility. And when these GMDs are sufficiently large in number relative to statistically stored dislocations, they act as obstacles to the statistically stored dislocations, and they increase the hardening. So you have these dislocation hardening mechanisms happening every time you have gradients of plastic strain within a small scale. And of course, if I try to capture this with conventional plasticity theory, like von Mises, I wouldn't be able to, I would always get exactly the same result, right? Because there's no length scale in my stress strain description, in my constitutive model. And the good news is that a good number of famous mechanicians have devoted their efforts to extend plasticity theory to small scales by developing what are called strain gradient plasticity theories. And the key step, I would say, in building these theories is that you define the plastic work or the flow strength, not only as a function of the plastic strains, like in a conventional theory, but also as a function of the plastic strain gradient. And in this way, you introduce to two-dimensional consistency a length scale into your model. So if this length scale is equal to 0, you recover Rollinius plasticity, but otherwise, by fitting this length scale to the experiments, you're able to capture, as you can see very well here, the response that you would expect. This smaller is a stronger effect, this inverse of plastic strain gradients. And one thing that I should emphasize here is that the length scale that is relevant is the size of the plastic zone. It's not the size of the sample. In this case, we're constraining the plastic zone with the size of the sample, but if you look at, for example, indentation, you again see a very strong size effect. Even though you are indenting a very large sample, it's just that plasticity is quite localized. You have a near indented. So it's the same thing as you would see in cracks, right? You would expect that in cracks, most often, not always, sometimes you have plastic collapse and there's a lot of plasticity. Most often you will have a plastic zone that is physically small, near your crack tip, and that contains very strong spatial gradients of deformation. So you would expect to see quite a lot of GMDs and plastic strain gradients playing a role there. You would expect to see these local hardening mechanisms that arise due to the plastic input. In fact, nowadays you can use high resolution EBSD and you can measure GMDs ahead of cracks and inclusions, and you see that you see plenty of GMDs ahead of cracks and inclusions. So those things are happening in there. So the first thing that we did was to take one of those strain gradient plasticity models and to simulate what were the crack tip stresses ahead of the crack. And we saw, well, the first thing that we saw is that far away from the crack tip, the stresses are the same as those that you predict with conventional plasticity, because, as you can see here, the moment your plastic zone is too large, then this term becomes negligible and you recover the predictions of conventional plasticity. But whenever you approach the crack tip, you have these big gradients of plastic strain, so you have these dislocation hardening effects that are elevating your stresses. So it seems that this could be an explanation for that conundrum that we have, understanding brittle fracture in the presence of plasticity. It seems that maybe one can get those stresses based on the fact that you have dislocation hardening mechanisms associated with plasticity. So we tried to do a more systematic study. For that, we decided to model crack growth. So we placed some cohesive elements ahead of the crack. Those cohesive elements are characterized by attraction separation law with two key ingredients. One is the strength of the cohesive strength, and then the other one is the fracture energy, which is the energy curve, this gamma naught. And based on this fracture energy, you can come up with two variables. One is the reference stress intensity factor at which cracking will initiate, and the other one is the size of the fracture zone or the plastic zone, which again scales with this fracture energy. So if you do a dimensional analysis, then you will see that your crack growth resistance curves will be depending on a number of non-dimensional sets, and this one in blue is the most relevant one, which is the one that doesn't show up in conventional plasticity. You have a length scale, that material length scale that characterizes your ability of your material to harden into GMDs, and then this R naught, which is a measure of the size of the fracture process zone of the plastic zone. So then when you simulate first the stationary result, so the crack is not growing, I'm just plotting the stress ahead of the crack. And here, as you would expect, you will see that as this ratio between the length scale and the plastic zone increases, then you get a higher influence of these plastic strain gradients, you get higher strain gradient effects, so higher stresses. Then we model the crack growth resistance curves. And again, as you would expect, you will see that as you increase this ratio between the length scale and the fracture process zone, you get a higher strain gradient effects, you get higher stresses, and you bring down the crack growth resistance. And what the next thing that we did was, if you look at these R curves, what you will see is that at the end you reach a plateau. This is what we call the steady state fracture toughness. So we can compute this steady state fracture toughness as a function of the cohesive strength. In this case, it's 4 times the yield stress, but we can move around. And as I told you before, the regime that we're interested in going all the way to 10 times the yield stress, because this is the theoretical lattice strength, this is the cleavage strength, this is the level that you need to reach if you want to predict brittle fracture. And first you see the result that you get with conventional plasticity. As we discussed before, our stresses are not high enough. There's no way we can mechanistically argue why we get brittle fracture in the presence of plasticity, because we're simply too far away. But the moment you introduce the length scale, you get an additional flexibility. And again, depending on this ratio, your stresses might be large enough such that you eventually hit this theoretical lattice strength. So it does provide a framework to mechanistically interpret what is happening in there. I think one point to emphasize is that, of course, where you are exactly depends on this ratio of the length scale versus divided by the fracture process zone size. The length scale is a material property that you can fit, like you fit the strain hardening exponent to a microscale experiment. It tells you how easy it is for the material to harden due to the presence of GEDs. And then R0 depends on this fracture energy, right? So you have a very ductile process, very ductile fracture process with, I don't know, a fracture energy of thousands of kilojoules per square meter. Then your L divided by R0 ratio is going to be very small, and you're going to be somewhere here. But if your fracture process is small, of the order of 100 joules per square meter, then this value is going to become meaningful, and then you can rationally interpret what is happening when you have brittle fracture. So it does seem to provide a good mechanistic rationale to understand why we can eventually reach those levels when we have a brittle fracture process. And this is, by the way, exactly the same that you did with this previous location dynamics. So if you go one step down, you will be able to see that you can actually hit those, under certain conditions, you can actually hit those brittle theoretical lattice strengths that you need to get brittle fracture. So we did we particularized this kind of general scheme to a few interesting case studies. The first one is a failure of a B material. These are the classic experiments by Ford and Fleck workers, where they had a crack between niobium and sapphire, and they saw that the crack propagated in a very brittle fashion, a very cleavage crack, a very sharp crack, but at the same time they measured quite a lot of dislocation activity in niobium. And then, of course, if we compute the cracking fields for those conditions, for the critical load at which failure was observed, then we see that with conventional plasticity, our stresses are far off. No way you can get atomic decohesion there. But if you take into account these gradient effects, your stresses are sufficiently large over a relevant distance to get to rationalize this atomic decohesion. Another case study is the low temperature cleavage, so cleavage of ferritic steels at low temperature. And here we use a Weibull, 3-parameter Weibull model to feed the data with both conventional plasticity and gradient plasticity, and we got very different results in terms of the Weibull parameters. But what I think is more interesting is that we computed the local probability of failure for a given Weibull stress, and we saw that the probability of failure was typically spread over tens of millimeters for conventional plasticity, while it was constrained to tens of micrometers for gradient plasticity. And from the experiments, it seems that the critical distance for low temperature cleavage is within tens of micrometers, so it seems to have been very interesting. And then last but not least is hydrogen embrittlement. This is quite an interesting problem. There's an entire session dedicated to this running throughout the conference. And the idea is that you have hydrogen entering your metal, and the hydrogen transport is driven by gradients of hydrostatic stress. You can see here the steady state expression. You have the hydrostatic stress inside of the exponential term. So it is very important that you get your stresses right if you want to know what is your hydrogen content. And what we see here is that when you run these coupled deformation diffusion simulations, what you see is the hydrogen concentration that you ever had with your crack tip is much, much higher when you consider strain gradient plasticity. And it's difficult to measure experimentally how much hydrogen you have near your crack tip, but the few experimental measurements that have been out there, they seem to report much higher hydrogen contents than what you would expect using conventional plasticity theory. And in fact, this is one of the examples. So these are some SIMS measurements of hydrogen content ahead of the crack tip. And you can see that only by using strain gradient plasticity, we're able to capture two things that you see in the experiments. One, that the hydrogen content increases ahead of the crack tip. As you approach the crack tip, you can see it's very high hydrogen content, nowhere near the conventional plasticity prediction. And the other one is that as you increase your mechanical load, you get higher hydrogen content. You don't get that anymore in conventional plasticity as your crack tip stresses are being constant. And one last thing that I want to say about the hydrogen embrittlement is that one of the interesting aspects of this is that one thing that hydrogen does is to reduce this fracture energy. And by reducing that fracture energy, you are changing the R0. So if I take you back to these steady state toughness curves that I showed you before, the same metal in the absence of hydrogen will have a very large fracture energy. It will fail in a very ductile fashion. So you are somewhere here in this regime. Your L to R0 ratio is very small. But the moment you bring hydrogen into the picture, as they see in the atomistics, these are traction separation laws as computed from atomistics, you can see that there's a dependency on the hydrogen concentration, and you bring down this fracture energy. So you're bringing down your R0. Your L remains the same, it's a material property, but your R0 goes down. And when you take that into account, you put 1 ppm of hydrogen, you see that all these curves shift. So that ductile metal that was lying here now lies here, because you have a much smaller plastic zone, a much smaller fracture process zone size, and you have a much higher stress elevation due to these GLD mechanisms. So this, in my opinion, provides a modern interpretation of the cohesion arguments in the context of hydrogen embrittlement. So that's all. I hopefully finish the time with maybe one good question by saying that, I will just conclude by saying that, first of all, we need to understand why brittle fracture happens in the presence of plasticity. Plasticity is telling us that the maximum stress that you get is 4 times the yield stress, but we have a lot of experiments telling us that we observe very clean fracture surfaces, atomic decohesion processes, which require stresses of 10 times the yield stress. We think that the most suitable hypothesis is that strain gradient hardening, this occasional hardening due to plastic strain gradients and GEDs are triggering these high stresses that are enough to reach the quasi-cleavage strength under certain conditions. We can use strain gradient plasticity to simulate those situations, to capture the role of GEDs and plastic strain gradients in governing the material behavior ahead of the crack tip. And this is particularly relevant in fracture processes that are where the critical distance is very close to the crack tip, as in hydrogen brittle, with the critical distances of a few microns ahead of the crack tip. And then finally, I will say that we have done analysis to see whether with quantitatively we were able to rationalize in a mechanistic fashion how B material interfaces fracture in a brittle manner, low temperature cleavage, and the hydrogen brittle materials, and we seem to understand quantitatively what is going on using this kind of a strain gradient analysis. That's all. Thank you very much for your attention. Thank you.